interferometric. People always ask, how do we know it's 30 nanometers? Well, we just reflect a laser beam, and because there's two surfaces, you can calculate interferometrically the distance. So you use laser interferometry and you get the distance ferrometrically, which is nice. So we can measure in this 30 nanometer region, and we measure fluorescence. So we just shine our laser beam in here, then we put on photon counters and we sit and we actually wait all night to get a spectrum like this. So you just set the experiment going, come back the next morning, and there it is on your oscilloscope, which is nice. And this is what we see. So if we look in a fairly thick region, so if we look in a sort of 400 nanometer region, that's lambda by 2 actually, you see these nice resonances, and if you're familiar with the rubidium spectroscopy, oh gosh, I've gone back to the beginning. This is very complicated. Let's see. Some randomness. Okay, there we are, back again. So if you're familiar with rubidium spectroscopy, you'll see that these are the excited state hyperfine splitting in rubidium 87 here. So this is the F equals 2 to 2, 3, and 4 transition in rubidium 87, and this splitting here is on a sort of 200 megahertz, something like that. And you can see they nicely resolve, which is one nice feature of these fin cells, that you get this Dickey narrowing effect. So if you did this experiment just on a bulk thermal cell, you would just see a very broad Doppler broadened background. You wouldn't resolve these hyperfine components, and you usually do that with Doppler-free spectroscopy techniques. But here you get it for free, just because these atoms are confined in a very narrow plane that's less than the wavelength. So you get this Dickey narrowing, and you can see these nice resolved lines. So that's the 87, there's the 85 lines. And then as we go narrower, firstly you see the spectrum broaden somewhat, which is partly because we have to crank up the number density, so there's other broadening mechanisms as well. But you see this large shift, and you also see a large asymmetry in the line. And that's exactly what you'd expect. So the shift is to this point here, this turning point, so we'd expect to see a shift to this value. And then the asymmetry arises because we also have atoms out here that are going to get larger shifts. So the fluorescence that we see way out in the wings here is from the guys very close to the wall, and the fluorescence we see at the peak here is from the ones that are right in the middle. So we see this asymmetric line shape due to this dipole-dipole induced shift. So this is the Van der Waals atom surface effect in our gas. And we're still working on this. We're trying to get quantitative data and really measure this C3 parameter and really confirm that it is a C3 and there isn't any other nasty things. So I think there's a big motivation to get atoms closer and closer to surfaces, and sort of 15 nanometers is sort of close to a record of how close people have got atoms to surfaces and measured something. So it's interesting to see what other perturbations, like is there charges on our surface and how clean are the surfaces and what other perturbations might we see. So one of the problems with extracting stuff, so we struggled to extract real good quantitative data from this, and the problem was the sort of convolution of the hyperfine splitting with this shift, and it ends up all being a bit of a mess. So we went to doing experiments on cesium. This is a cesium D1 line, which is really nice because they're basically individual lines without there is hyperfine splitting, but the splitting is now much larger. So this is now the hyperfine splitting of the excited state, which is a bit more than a gigahertz. So this is one of the hyperfine lines, this is the other one. But you can now treat these things as almost isolated lines. And again, you can see the shift. This is in 150 nanometers, so not quite as extreme as the other data. There's a number of other problems with this, that because the wavelength's longer, the photon counters aren't as good, so you don't get quite as good signal to noise. So we've been studying slightly longer lengths. But again, you see the shift, and then in this inset here, there's a nice, you can see how this is the line center, and you can see there's a shift of about 20 megahertz. And you also see the asymmetry here, and that's the other line, which is also asymmetric. And now you can do a funny thing, which is that you can map this asymmetry exactly into position from the surface. So because we know this C3 over R cubed law, we can basically map these frequencies into positions from the shift. And so then you can see how close can I see an atom to my surface. And you can see that's done here. And you can see that this scale is very sort of non-linear. So it's like 50 here, 20, and then it's not going down very fast. So it's 13, 12, 11. And so if I'm right out in this wing here, I'm at 11 nanometers from my surface. And we would claim from our analysis that we can comfortably see atoms that are 11 nanometers from the surface, but we wouldn't claim to see anything closer than that. And actually, when you're this close, you really have to worry about things like your surface roughness, because if your surface roughness is 5 nanometers, then what does it mean to say that an atom is 11 nanometers from the surface? So we're actually quite pleased with this. This is quite recent, just before Christmas data, and we quite like that. And maybe just, because this is a school, so I put a lot of pressure, and Hannes will probably verify this, on all my students to make good figures. And they have to go back. Some of them hate me. So there's two types of students. The ones that hate me because they think I'm pedantic, and I just keep telling them to go back and make the figure better. And the others that sort of sign up to this fully and will spend hours and hours doing figures. But this is I think this is an example of a very good figure, and I like it because it's taking it to the next. Not only is there just one inset, but there's two insets in this figure. You can still read the small inset and get some useful information from it. So to me, that's an example of a good figure.
How do you describe it in the caption?
Oh, the captions end up being enormous. The thing is, it's easy to write a paper, right? Because you just. So when we write papers, we just make the figures, and then we write the captions. There's no space left, so then we're done.
Yeah. So can I ask a physics question?
Yeah.
So actually, to be honest, I don't quite. This figure looks great, but I don't quite understand what exactly is plotted. So basically, what you plot is a peak.
It's a fluorescence. So all we're doing.
You plot kind of the height and the frequency of the peak?
Yeah, so what we're doing is we have a laser beam that we shine through here, and we scan the frequency of the laser beam, and then we just measure fluorescence as a function of the laser frequency. So if there was no surfaces or no bad things, we would just see, we'd just see single Lorentzians here with either the Doppler width or some Dicke narrowed peak.
Yeah.
But that's not quite what we see. We see that we know where the resonance is because we have a reference cell, so we can calibrate our frequency axis very well from the reference cell. So this is where resonance should be, and we see that the resonance is shifted and that there's an asymmetry in this. And then we fit this curve with the C3 over R cubed, where R is the distance to the wall. It's actually fitting it to this curve here. So we think this is the potential that we'd expect to get. So we basically, if you convolve your Lorentzian with this, then this is the line shape that you would, that's the line shape that you get. So that's like a Lorentzian or a Dicke narrowed peak convolved with this potential.
Okay. The big curve, and what's a big curve?
The big curve is all we add on the big curve is to then, we can basically, from these detuning values, we can extract a distance. Because basically there shouldn't really be any signal out here at all, and there's only signal out here because of the shift. And that calibrates back into a distance. So we can sort of...
the big curve is the same as a constant.
It's the same, yeah. The reason why we put that, the first, so it's actually my postdoc that did this curve, but he was my student, so he knows how to make figures. But the first figure he did was just this one, and then you see that, you might say, well, you can't really see the asymmetry, and you need to see both lines to see that this tail here comes from this peak, and then you need to see this inset to really see that there's an offset because it's too small here and things like that. Yeah. Okay, so that shows we can see some effects of dipoles in cavities. So we've talked about 1D arrays, and I sort of presented an experiment a bit in the Rydberg manifold on a 1D array of these blockade spheres and hopping. Now I've given you a 1D array analog, cavity analog of a 1D array, which is a dipole in a cavity, however bad the cavity might be. And then we can start to talk about 2D arrays, and this is obviously the thing that we'd like to go on to. So already, if we go back to Tom's talk and some of the earlier talks on resonance, basically the systems that people have in dipole systems, and I guess the system Matthias has got, is 3D random arrays, which is very complicated, right? So we're trying to build this up to these complicated systems where we get 3D random arrays by considering one dipole, two dipoles, 1D arrays, 2D arrays. So let's go to 2D arrays and see what happens now. So once we've got a 2D array, then we can start to think about So we can have 2D regular arrays, then we can have 2D more complicated arrays, and then we can have 3D patterns and irregular 3D things. So fortunately, the 2D array looks pretty much like the 1D system. So this is now, we've got a grid of dipoles separated by A, and we do the same thing, we calculate shifts and whips of the resonances as a function of this lattice constant of our array. And this was the 2-dipole case that we had before, and we see these sort of oscillations, which is the e to the ikr in the long-range part of the dipole-dipole interaction. And then, as we saw, as we added more dipoles, these things just get sharper, so we get resonances of order of the wavelength when the dipoles are separated by the wavelength. And now as we go to a 20 by 20 array, the same thing happens. But you just get more resonances, because now you get resonances on the diagonals as well as these guys. So we actually get extra resonances. So this is slightly more complicated. But basically the physics looks very similar. And one thing that's interesting here is you can take one of these arrays and you can say what's the transmission through the array as I vary the separation. And you calculate a curve like this. So you see these resonances. And I think that's interesting because that's an experiment that could be done. So if you have like a Mott insulator, a single layer of a Mott insulator, so you've got now this 2D array of atoms, and you shine on resonant light, and then you ask what is the transmission through this Mott insulator state as a function of the lattice spacing. If you could vary the lattice spacing in some nice way, then you could get out this curve here, and you'd see these dipole-dipole induced resonances, and there's a very big one here. And then sort of bad things happen when you go too close. Basically everything shifts off resonance and then it becomes transparent again. So I've called this rubidine because for a long time we were interested in graphene and how the optical transmission of graphene is related to some fundamental constants. And we were saying, what's the optical transmission of rubidine? Well, now we've calculated it and we understand it. And this is something that would be nice to do experimentally, so maybe not for us because we don't have a Mott insulator, but for someone like Marcus Greiner, or Emmanuel Bloch, and so the Marcus Greiner parameters of this, he's at point A here, so his lattice constant is here. So he's actually right in this interesting regime where there's a very rapid change in the transmission as a function of lattice constant, and the change is massively induced by dipole-dipole interactions. And this curve here is the curve you would get if you neglect dipole-dipole interactions. So you can see that dipole-dipole interactions are massively modifying the optical transmission through a Mott insulator in the regime where people are typically working. So that would be an interesting thing to study experimentally. Okay, so that's all I'm going to say about regular arrays, and now we're going to go on to the horrible topic of random arrays. So random arrays are really, really complicated and really hard to understand, but we'll at least get some small insights. So we've had these regular arrays of dipoles, and now I'm going to have random 3D arrays. Now the first thing is looking at these pictures, which is a sort of all these shifts and whips as a function of separation. Now the first thing you realize about a random array is that you've got a range of separations. So we now have to average over all possible separations. And just looking at this curve, if I average it, you can see that everything's going to average to 0. So it's as much positive as negative. So you don't really expect to see any shifts or any changes in anything when I average over a random array. So if I now solve this coupled dipole equation for all my dipoles, every dipole is interacting with every other dipole, and I ask what's the spectrum, then you get a spectrum that looks like this, and as we increase density it goes up, but it doesn't shift. So all these shifts and stuff that I've been talking about that we could measure and look for are not there in a random array, apparently. And this is a calculation by Juha Jalanainen quite recently where they show that there is no shift for a random array of dipoles, which is quite nice. So we did an experiment on a random array of dipoles, again in our simple cell. So we've got our cell now. So before we were looking at the atom-surface interaction, but now we're looking at the atom-atom interaction, so the dipole-dipole interaction. And we can do this just by cranking up the temperature so that the mean spacing between the atoms is much less than the spacing between this cavity. So we neglect now the cavity effects, the atom surface shift, and now look at the atom-atom shifts. So here's an absorption spectrum. Again, you see these dicky narrowed peaks. This is the rubidium-87, the rubidium-85 again. We have a model, and we do residuals, and we say, okay, we're happy, we understand all the physics. And then we crank up the density, so that's the old low density scan, and then we crank up to high density, and you see everything is massively broadened. It's all very broad. That's because of the dipole-dipole collisional broadening. But also it's shifted. So if we just do our model and we don't put in a shift, that's the predicted curve here. So this dotted one. But we see the data's over here, so we have to add in a shift to explain our data. So there's some new shift that's appeared in our system that's not in our model. So what is it? So this is going to be what we referred to earlier as the cooperative Lamb shift, or the dipole-dipole shift. So now we're in a bit of a problem because we've got theory guys saying there isn't a shift, and we've measured a shift. So here's our actual experimental result, and we measure this shift as a function of the thickness, because we've got this variable thickness, so we can go in and measure the shift as a function of thickness, and you get a really nice curve, which is a sinc function. So we measure this shift as a function of thickness, and there's actually a formula, and you can find this formula. Everything was done in 1973, turns out. Almost all physics that we do was done in 1970. I mean, me. All the physics I do was done in 1973, and the next year I'm going to do physics that was done in 1974. So anyway, there was a theory predicted in 1973 that had this nice curve, and the prediction, that's the theory curve, right, this line here. So, excellent, we were very happy, we've confirmed this theory, but then everybody tells us this theory is wrong, so that's because they neglect stuff. And then people like Yabanainen said there is no shift. So now we've got a big problem. He's got a problem too, because we measured it, and you can't, either we've got it wrong, or he's got it wrong. So we've got to figure out why is there a shift in our experiment, but it's not there when you do the theory properly. So here's the sort of brief answer, I guess if you really want to know more details, you can read the Yabanainen paper. So this is the model that they use. It's just classical dipole-dipole interactions, and there's no shift, as we saw earlier. And then we have to think about this dipole-dipole, and we can go back to this hopping picture if we like. We can go back and think about hopping, we can go back and think about multiple scattering. What's hopping? Well, photons come in, they go off this dipole, they go to that, maybe virtually, but so real photons come in, then they virtually hop around between all these different dipoles, and then they come out again. And that's somehow what this whole dipole-dipole interaction is in terms of virtual photons. So we can think about it as multiple scattering, and you can think about orders of this scattering, or orders of this hopping, if you like. So how many times can my photon virtually hop to another atom before it sort of comes out again as a real photon? So rather than writing this equation in this form of all these coupled dipoles, you can write it as a sort of power series, and it's a kind of multiple scattering expansion in the sense that each term is one more scattering event off another dipole. So the first order term is I come in, and then one virtual dipole, one virtual photon goes to my next dipole. So I've excited two dipoles, and then there's a dipole-dipole exchange, one hopping event if you like, and that's the first order term. And then the next order term would be that guy coming back again, so that this one hopping across and coming back. So this is the second order term, and then you could write a whole power series of this. Now the thing is, in this basic theory, all these sort of orders are of the same order of magnitude, so there's no sort of attenuation of these terms. So all these terms contribute, and it turns out because all these terms have different phases, so the first one has an e to the ikr, because it just has one lot of, there's a g here, which contains the spatial dependence, so it has one lot of spatial dependence. The next order term, I have to go there and back, so I get e to the i2kr, and so on, I'll get e to the i3kr. So now if you imagine averaging over all these things, you can see how they're going to average out of phase. It's going to be very hard for me to find a distance, or only at the very special condition that I'm separated by the optical wavelength, are all these terms going to add constructively, but most of the time they interfere destructively and average to zero. And that's why I get no shift. So when I take this whole series, I get no net shift of my resonance. So that's what would happen if there wasn't anything else going on in our system. But actually, in addition, so in our system we have thermal motion, we have Doppler broadening, and this is inhomogeneous. And this means that the dipoles don't stay the same dipoles for very long, because they're moving about and changing velocity. So although I might get this process, by the time I've done this, then my dipole's moved away and I can't do it anymore, because it's now somewhere else, or another dipole's coming along that's moving at a different speed. So this is basically this Doppler effect, or the motional effect, is an inhomogeneous broadening. So then in this power series, you basically have to add a factor. There's this broadening factor, which would be my natural width, which is the scale of the coupling, over the width of the broadening. So the first order term would so I get some attenuation, that's basically the ratio of these widths, and then this would come in as the square and the power n on the nth order term. So now this series is attenuated by this broadening effect. So the probability of getting these multiple scattering events or exchange of photons or many photon hopping is basically attenuated by the fact that we have a thermal gas random motion. And so we have to truncate this series now. So we truncate this series at the first term, and this is the only one that survives. So Yavanainen's done that, so he crossed off all the terms and just leaves this term in, and he gets these dots. And you can start, before he had no shift, so he just had a straight line with no shift, and now he's got a shift. So this first term gives us a shift, and it gives us a shift that has some thickness dependence when you do it for a slab. And this is basically our result, which agreed with this earlier theory paper, and you see it follows the same curve. So the only difference now is it agrees apart from an offset. So we don't understand the offset, but basically we've learned something, because we've learned the importance of inhomogeneously broadening and the suppression of these multiple terms in this multiple scattering, leaving us with this first order term. And we can think of this first order term as a mean field. So this is a dipole, a mean field now, which appears only when we don't get many orders of the scattering. So when we don't get high order dipole-dipole correlations, we can have a mean field. And that's what we're likely to see in a thermal system. What is this mean field? Well, it actually has a name, and it's frequently called, and it's something that's very old, it's called the Lorentz mean field. We can call it the dipole mean field. It's analogous to what's called the Lorentz local field that's been studied for 100 years in solid state systems or liquids or even gases. And we can write it in this way when we do classical electromagnetism, that we've got our original field that we apply, and then the total field at some dipole I is the field that I apply, plus another field due to all the other dipoles. And we characterize our medium as a net polarization, which is dipole moment per unit volume, and we add this new field due to all the other dipoles as a mean field. And this gives us the same kind of shift, or the same answer as we'd expect here. So that the 1973 result was basically built on this idea that we could do the Lorentz local field idea and get this mean field, and then we would get this curve out. So we can now see when do we expect to see mean field, when do we not, and we need homogeneous broadening, inhomogeneous broadening to see the appearance of this mean field. How am I doing for time?
-1.
Oh, I've already finished. So I haven't. I think I've only done. I don't know how much I've done, but we haven't got to the end. But anyway, given that we're running out of time, let's just finish on a little bit of an aside. Given that we heard some nice stories of important people in the past. So this business of the mean, I said it's called the Lorentz local field, and the origin, it's also connected with this Lorentz law. And this is incredibly confusing. I still find it confusing, so I thought I'd better make a slide trying to figure out who was Lorentz and who's Lorentz. Now, Lorentz was from Denmark, and he discovered the Lorentz law in 1969. And Lorentz discovered it in 1970, so 1 year later. But it's always called the Lorentz law, and then often we just talk about the Lorentz correction and stuff. So the Lorentz gets forgotten, which I think is sad. But I think it must be because Lorentz got more famous and won a Nobel Prize, whereas Lorentz didn't. But let's say a little bit about both of them, because they both did really nice stuff. So Lorentz was Dutch for 1853-1928. He won the Nobel Prize with Zeeman for the Zeeman effect in 1902. He's probably most known for the Lorentz transformation, because we all do that in our special relativity course, and the Lorentz force, of course. And interesting, I read on Wikipedia yesterday that he was offered the job at Leiden. He was offered the job in Amsterdam that Van der Waals took. So this was really a golden age in the sort of for Dutch physics with all these guys, Zeeman, Van der Waals, and Lorentz, and they were really doing amazing stuff at that time around the turn of the century. So that's Lorentz. And then Lorentz is, I'm now a big fan of Lorentz, so I'm going to start calling it the Lorentz law. So Lorentz is Danish, and he was in Copenhagen, and he was funded by the Carlsberg Foundation to study light propagation through media, i.e. beer. So that's all our dream. So I'm going to now apply to the, considering that I also like light propagation through media, I think I'm going to apply to the Carlsberg Foundation to see if they will support me too. And he's probably most famous for the Lorentz gauge, as well as this law. So this is how you have to remember these two guys. So both very nice contributions. And I'll probably pick up on that in my last lecture, and we'll talk a bit more about this and some other examples. So I think I better stop there.